Okay, everybody, I think we're going to try to get started. Welcome to the afternoon session. First up will be Randall Stewart. He's with Cisco Systems, and he'll be talking about kernel locking, how to profile code that you have, and how to make it better if there's a problem. Randall?
Hello. Thanks for coming. So I'm going to talk, some of you will be bored by my talk, because you've probably done some SMP or threading type things, but hopefully there'll be some new things for all of you. Push the right button. So why do we lock? Well, now we have SMP machines. This machine here that I'm typing on has 2 cores. I have a couple of servers in a rack back at home that are 8 cores. And on my desk, I have a prototype board that's that big that is 16 cores. Soon we'll have 32, 64, 128 cores. I've heard rumors of 64 for sure, and I have no doubt that we will see 128 cores in a CPU soon. So this poses some interesting challenges. When we get an SMP kernel like FreeBSD, we have to contend with how do we synchronize the different CPUs and make sure that the data we look at is consistent. And so each OS has their own method to do this. I mean, a common thing in application space is pthreads. Pthread and mutex is a common thing. FreeBSD, like all of our OSs, have come to deal with this through a mutex mechanism. And it's a real common thing to do, and you'll see mutex all over the FreeBSD code. So what does a mutex do for us? It provides a simple gate that says, I grab this thing and I hold on to it, do what I want to do to change things, and no other CPU will actually try to muck with what I'm changing until I release the mutex. In userland, we use pthread mutex. That's the most common. I think there are some other, but I think the POSIX version is probably standard in every operating system, and most application code will use it. In the FreeBSD kernel, we have something called MTX, mutex. It's pretty much is the same as pthread mutex, only it's specific to the kernel. The structure, you basically have a structure you declare. You must initialize the structure before you start using it, and then you call lock and unlock on it to have exclusive access to whatever your lock is protecting. So in SCTP, we decided to go, we went with real fine-grained locking. In particular, we wanted to have multiple cores being able to work on the same connection. And we did this with having quite a few different mutexes. There are probably, in any SCTP association, at least 4 or 5 mutexes that get pulled in and at some point locked or not locked. One of the common ones we have is for socket sender. So we have a socket level application program that's sending data, and the data is going to go into a queue. And we have the interrupt task that is possibly receiving SACs and processing out and sending packets out. So we put a mutex on this queue so that the 2 sides can hopefully run on different CPUs and contend for the queue. So the socket sender would grab the mutex, add more data, release the mutex. The interrupt task, when it finds it gets a SAC from the other end, can now send more data. We'll grab the mutex, pull data off, and release the mutex, and then send the data onto the network. Very effective way to coordinate between the 2 processors. Okay, now if I can. So this simple scheme allows us to coordinate 2 CPUs, but there is a downside to it. If you think about the 2 CPUs running, if I'm holding the lock and you want to use the lock, then you're going to have to wait. So your CPU will probably go off and do something else, but you're not getting as much parallelism as you would like. So what you look at that as lock contention is what it's called. So I contend for the lock. Kirk wants the lock at the same time. We both jump for it, and only one of us gets it, and then one of us has to wait. So lock contention interferes with your ability to run parallel and keep both processors working on your problem that you want. So it becomes a real problem when you have lots of parallelism that you want to input in a process. So in FreeBSD, we have ways to figure out how much lock contention there is, because when you first design something like I showed you before, you don't think about it, you just want to make sure that the data structures are same. But once you start running it and you see performance doesn't maybe look as good as you'd like to figure out where you should concentrate your effort to reduce the lock contention, if there is some. So FreeBSD has a nice little thing added. I think it was 7.0 added it fully. It may have been traceable, but it may have been in 6, called lock profiling. So this doesn't work in user land, but it sure works nicely in the kernel. So what you do is you build a kernel with the option lock profile. So if you look here, I've added to my kernel configuration options lock profiling. And I go through and build the kernel. What this does for me is put into the kernel some a toolkit, if you will, for measuring lock contention. So once you reboot and bring up your kernel, you're able to look at the syscontrols and you'll see things like debug lock prof enable, debug lock prof acquisition, and other nice little things. Basically, when you start the kernel, the lock profiling will be turned off because it does itself take resources, because it's got to count all these locking events that are going on. So when you're ready and you want to profile your process, you get everything set up, you get all set to go, maybe your commands typed in 2 windows that you're going to run, and you go in and you twiddle this thing I have highlighted in red here, debug lock prof enable. So I do a syscontrol minus W, debug lock prof enable equals 1. That immediately turns on lock profiling. So now all locks in the system that are happening, and there's a lot of them, that go on, whatever you're doing is going to turn away. And you hit your 2 carriage returns on your windows, and now you run your process, your test, and then as soon as you're done with your test, you're probably going to change that lock syscontrol back to 0 because your performance is kind of slow while that's going on. Once you're done with running your test to run, then you do a syscontrol minus A and dump it to a text file. Okay. Inside that system, the reason you want to put it to a text file is it gets real big with lock profiling on it. There's lots of stuff that will show up. So then you use VI or Emacs, whatever your favorite editor is, and you go in and you scan down until you find this set of symbols here. You'll see something that says max, total weight, total average, weight average, count hold, count lock, and name. And lots of numbers will follow that. And of course, you're going to be looking for your specific locks that you're interested in which to profile. Now, before I go into showing you what the SCTP results I did when I first approached this, I'll describe to you basically what those headers mean. So max is the maximum time that point, whatever is being showed, waited in microseconds. So how long it had to wait. Total would be the total hold time that lock was held. So if you saw some number in the hold time, that means the lock was held for that many microseconds. All the values, I believe, are microseconds. The wait total is the total accumulated wait time. The count is the number of times that at that point in the code you grab the lock. Now, the ones that are starred are the ones that I focus on, because some of them I don't care about. Depending on the type of measurement you're doing, you're going to look at different of these values. Average is the average hold time in microseconds. That's the one I didn't care about, and for this talk I don't really need to concentrate on. It might be something you're concerned about if you see you're holding a lock for too long, because locks really should not be held for long periods of time. Some in this room have stated they should be held very many periods of time. In a class I took once. But sometimes they're held for long periods of time for valid reasons. Weight average is the average time that somebody else was waiting for the lock. Count hold is the number of times this lock was held when someone else wanted it. This is a key thing. So if you're holding a lock and someone else wants it, that counter is going to get bumped. And count lock, another key for lock contention, is the number of times someone else held the lock at that point when you wanted it. So my code wanted to go lock the lock, and it was held, so I had to wait. So these 2 hold counts are very critical to figure out where I have lock contention. And the lock name is cool because it not only gives you the lock, it gives you the line number in the source code where the lock was at, which is really neat. And so But that also means every lock will have possibly multiple places that it shows up because you have it locked in multiple places in your code. Now, in our earlier example, here is the same queue that I was talking about, and we have this send mutex, as it's called. There's actually another one on the receive side as well, just like it. And you'll notice some counts here, and I've only highlighted the ones in particular that are of interest. The count of times it was grabbed, the count held, the count locked, and then you notice the file name and the line numbers. Now, I doubt that these line numbers are valid anymore because I did this probably 8 months ago and the code has changed some. But these at the time were where those locks were actually being evoked. So, an important thing to note is this one in red here. Notice we have 12,240 times that we have grabbed the lock, but notice it was count hold. Well, I was holding lock, and 5,571 other times somebody else wanted the lock. That doesn't sound very good. And it was locked 551 times that I asked for the lock. So this SCTP output.c, the top two actually are in the actual interrupt transmission type routine. The bottom ones with high number of source codes are where I the sender, am sending down. And so you notice the sender is oftentimes waiting for the interrupt task to send some data out. Now, this can have a bad effect because if you're trying to fill the pipe for the transport to send out, it very often will run out. And actually I was seeing this. I would have the transport would run out of sending data, and we'd have idle periods because you lose your act clock. So this contention was causing problems so that I couldn't keep the pipe filled, if you will, because I would run out, the guy would drain the queue and there'd be nothing else to send. He'd release the lock and now, boom, the guy would send some more down, and it would take another sack or something else to get things moving again. And so this lock contention was harming performance. We were looking at 45% of the time it was being held when someone else wanted it, which is really not a good thing to have happen. So I had to look at some measure or some way to minimize this. This toolkit was wonderful for discovering the problem. Of course, it doesn't solve the problem for you. You have to figure out how to solve it yourself. So you'll note also that here's the victim, the guy that had to wait most of the time, but of course, occasionally he held it as well. Now notice, these are all different points in the same output routines and the same transmission routines. Even though there are different points in the lock, but different places. And you can see there's really only 2 places that are heavily locked back and forth. But they're effectively the same place. So I had to take a step back and look at the problem in more detail. We have this simple mutex, and if you look at this queue, it's really a tail queue. Tail queue is a TQH first and a TQH last. Okay? So the question really became, how do we preserve sanity, keep this queue sane as we add and delete things from it, and yet reduce the amount of lock contention? So there's some things we can look at, which is the socket sender is always appending to the tail because you always drop it at the very end for the next new one I want to send out. And the transmitter is always pulling from the top. He wants the head. So we actually have a first and a last here. So that could possibly help us. And obviously, of course, the whole message has to fit in a PMTU, so it does cause some shrinking. So when I have a large message sitting there, I might only take part of it. I might not take the whole thing because it's got to fit into a PMTU band. For non-network, PMTU is pack MTU. So when I send on the internet, generally 1,500 bytes is as much as I can pack in a frame going out. And it's actually a little less than that. So how do we reduce lock contention? So after looking at this and thinking about it for a while, I said, well, let's look at the sender. The sender never knows if the transmitter is active. So I'm going to write some data out. I don't know that a SAC's coming in on another processor and he's busy processing. I have no way of knowing that. And I can never be sure if the list is empty or has entries on it at the point when data is being added. So, and we're only using TQH last, but without foreknowledge that the sender the transport is actually doing something, you really can't do a lot. I've got to have a lock, in other words, in this structure. There's no way the guy adding data to the queue cannot lock the structure. It's imperative that it does. But what about the transmitter? We can kind of look at the transmitter, and here's an example of our queue filled up. We've got a head entry, and then we have next, next, next down to null. The transmitter knows some things that can help us in this reduction. First of all, it knows if it's going to pull something all the way off the list. I'm done with it, I've emptied it out, I can pull it. Okay? It also knows, if you look, dig down into this entry, this is actually a pointer to a series of MBUFs. Okay? So it may be only taking part of the data to fill an MTU. It may be taking the whole thing. Depending on that, it can figure out whether it needs to lock or not. So in one case, here, where there's other entries, even if the guy comes in to add more to the end, while I'm busy working on the head of the queue, I don't need a lock, because I know I'm here working here, he's adding to the tail, so I won't interfere with him adding to the tail if I don't do a lock. However, if I'm at this point and I want to take this entry here off, I've got to have a lock, because I don't know for sure that the guy is going to send just as I'm pulling it off. So in this case, I don't need a lock. And in this case, I do. Does that make sense? It's a little complicated, but if you think about the way that we're adding to the tail, it makes sense. And then to make it even more interesting, when I'm in this case here, if I'm not going to remove the entry from the queue, I can actually look at the structure and say, you know, I'm not taking all the data, and I add only full MBUFs, or MBUFs at a time. The cinder adds a group of MBUFs all at once. So it's possible that I can look at it and say, I'm not going to take it all because it won't fit in a PMTU. So he's going to add to the tail of the actual MBUF chain, because there's a pointer inside this, there's a tail MBUF pointer, which I won't touch. So I can safely not lock, even in this case, when I'm sitting like this, but I'm not taking the whole thing. Now, if I'm taking the whole thing, there's actually a flag in here that says the sender has finished adding to it. If I was to take the whole thing and have to remove the entry, I would still have to lock. But in the case where I'm just going to transmit some data, I can't fit it all in an MTU, I don't have to lock in this case. So by looking at the transmitting side, the guy draining the queue, I can make some special allowances that make him so he locks much less. So I went back in, rounded around, and played with it. Found some interesting things that I had to, stumble upon. Which one of the things that tripped me originally was when you looked at the length, because in the second shortcut, I looked at the length in the wrong place, which meant that I got it wrong a couple times, and I found that out the hard way. But basically, if you look at the length first and make your decision, you'll never go wrong, because what will happen if you look at it first is you might see that it's shorter than it really is. The guy added more, and no, I might take a lock that I shouldn't take. I wouldn't have took. But what I was doing is looking at the length later, and that caused a problem because the addition got added before and I made a decision not to lock, and then it wasn't. So you have to be real careful, basically, when you start playing this game of not locking. And of course, atomic add int is essential. You have to do an atomic add to the length on both sides to read and add and subtract from it. As long as you're doing that and you're careful about the order, you can even get by with the second stealing. The earlier one we were looking to see whether the next one is null or not is easy. This one's difficult. So when it goes to adding data, don't get the lock unless the size of the copy will exhaust the MBUF completely. This allows the guy to continue to add. When the transmitter decides to remove an entry in it, we'll only lock if the next pointer is null. That became basically the rule of what I did. Went back to the code, I played with it, and then I remeasured to see how well I'd done. So these are the new numbers after I had munged on the code and played with it a little bit. And you'll notice the numbers are significantly different here. Now, you'll also notice if you think back to the other thing, there was 3 down in yellow. In the process of collapsing this, I removed one of the locking points. Now, in reality, you sum them up and they come up the same. It's the same amount of locks going on, except for we have a lot less locks. So the number of times we hit that line of code is there. Notice the number of times the top 2 have almost no locking hitting. Before they were 30,000, something along that range. And the bottom time, now remember the sender that adding data is always locking. That's this guy down here in the yellow. You notice he still has a high number of times that he's locking, but he has no contention hardly at all, because the other guy very rarely locks. Now there's still a high percentage here. I mean, if you actually calculate out the percentage of contention, it's fairly high, but the difference is I don't do it 12,252 times to have contention. I only have contention 632 lock requests. So that makes a huge difference. Even though the percentages are high, it performs much, much better. So what's the conclusion of all this? Well, if you think about your data structures carefully, right, you first, has been quoted to me, make it work, then make it work faster. Okay? So you first take the simple approach, do the locks like I did, then you go in with a tool like mutex profiling in BSD. You figure out where the contention points are, examine your data structures very closely, and then see if you can find ways to escape doing locks and still keep your data sane. I wouldn't recommend going in, I would not recommend going and trying to do this first. I would say get it to work first, then figure out where to get the locks out, because there's nothing worse than having a lock bug. They're very, very difficult to debug, where if you're not locking, you should. They're hard to get. But these mechanisms are very useful. You can use them in user space as well. This same mechanism will work with a pthread mutex that would work with a kernel level. Now, I don't know if there's any types of measurement tools in pthreads to make it so you could measure this contention, but I know that the mechanisms themselves would work in a user application space. Really, I love the mutex profiling. It really is a great assistance, and I don't know who committed it, but I owe them a beer. Now, of course, no two problems are the same, but you can use these same concepts in user land. There are a couple other things that you can do in kernel land as well, but this is a caution slide. You don't want to do this type of thing unless you really are cautious and you really take it that you're doing very, very small amounts of work in this period. So you can, in theory, for example, have an array of free queues, one for each CPU. And when you come in to free an item, you do a critical enter, figure out your CPU, insert on that list, and then critical exit. What critical enter, critical exit does for you is it says no one will be scheduled in here and preempt you. You really need to think about doing this. I mean, device drivers will do this type of thing. It's another way to reduce lock, so you don't have to do a lock and you can avoid a lock. I don't do this, I think, in any of my code, but it's something you can consider if you're in a device driver and you need to get around or get away from having to do locks, because locks tend to be a little bit heavyweight. But again, I say real caution is needed when you want to do this. And of course, this would not work in user land. This would be something only for kernel space. And again, with extreme cautious, get some senior person to help you review it. I mean, before I'd even put something like this in, I would ask someone like Warner or Robert or Kirk for help and say, am I doing this right? Because it can cause real problems. And that is the end of my talk. Done way early, which I thought I would be. Do I have any questions?
Did you measure any, or what is the real world benefit from using the lock?
That's, you know, okay, so he asked what was the real world benefit from reducing the lock contention. Basically, I could get more data through a 10 gig pipe. Okay. It went from about 2.5 gigs to 4 gigs. Okay. I tweaked it up to 5 gigs now, and I did a different bottleneck, but I can get 5 gigs on a shell seal across SCTP at this point. So there is some measurable benefit. I mean, and the reality is I've actually now to the point where I can regularly see two CPUs on each side of a connection working on the same association. And association is a word for connection in SCTP, for those that don't know that. Another question?
Oh, if you know, then I would know, how about the overhead when you enable the lock profiling feature?
I didn't even look at how much. When you do it, the machine slows down. It doesn't slow down as much as turning on witness, for example. but it does slow down measurably. I believe, because I think back 6 to 8 months ago when I did this, the transfer went from, on 100 megabit Ethernet, it went from like, full 100 meg down to like, a third of the transfer rate. So it does put an overhead in for the measurement. It's basically, it's going, every time you do a lock, it goes through a bunch of things to see who else is waiting, and adds some counters and does some other things. So, and that includes, it's not just your code, it's the whole kernel that's doing it. So every lock in the kernel, so that's why I said syscontrol to a file, because it's huge. You have all these locks that you never even knew existed, and all of a sudden start showing up with their source code line numbers and file number. And so you really want to do this in a very area that you're not going to, performance isn't the issue when you're not worried about performance. You would never want to turn this on in a production machine. Now, even just having the code enabled without turning it on slows the machine a little bit. But when you hit that syscontrol and make that 1, performance goes quite a bit down. It's not as bad as Witness, but it does kind of go down because it's doing a lot more accounting. Other questions? Yes?
I think you test the result of lock contention on SCTP communication. So I'm very interested in the throughput performance improvement before and after lock contention. In our observation, current SCTP can work at 300 over 300 megabps. I also think the throughput before the improving lock contention.
Yeah, well, I don't really have any solid numbers, but I know I can get on my 8-core machines 5 gigabits through a 10 gig pipe.
Yeah, 5 gigabps.
5 gigabits through a now that's with an 8-core machine. So there are 8 cores. Now, in reality, only 2 of them are working on each side. I've got a sender and a receiver, and there's 2 cores active on the connection. And actually, the bottleneck, I can't get one connection over that, but if I add another connection, I don't get more performance improvement, and that's because the Chelsea thread that actually running the driver is the thing that's the bottleneck right now. And actually, I plan on adding a thread pool that will actually make it so I could add 2 connections and get the full 10 gigabit. But there are some things you have to do to tweak SCTP for that to get that high-speed measurement that I was getting.
Yeah.
Yeah, you can definitely get 300 megabits. You should be able to get more than 300 megabits on SCTP. So.
Yeah, thank you.
Other questions? No? Thank you.